Okay, so today we're going to continue our lecture. So we're going to talk about a buffer overflow example. So here we have our main program, right? In the main program, we define a buffer of 400 bytes. Then we define a file. We read in a file. The name is a bad file. So apparently, when you read in from anything, from external sources like network, right? Like the console. So all your input will be considered to be untrusted. So then we read in 300 bytes from the file into the buffer. Because the buffer is 400 bytes, so there is no buffer overflow here. Then we call the FOO function. So here is the definition of the FOO function. In the FOO function, there is a buffer of 100 bytes. Okay. Then we use string copy to copy from the string into the buffer. So you remember, so the string could be as long as 300 bytes. But you can actually, it's possible to write more than 300 bytes into the buffer. So because in C, string is terminated by 0, right? So string copy will continue copying from the source buffer until it met a 0 byte. So because the buffer is only 100 bytes, right? So the buffer can be easily overflow when you try to copy 300 bytes. So here is the memory layout. Stack goes down. So this is the high address. This is the low address. When the main function calls the FO function, it pushes the string onto the buffer. If we go back here, so the string will be the buffer defined in the main function. Okay, then it will issue a call function, say call FOO. This will be our assembly instruction. So the computer will automatically pushes the return address to the stack, right? So in the FO function, normally it will save the previous frame pointer or the EBP, right? This is done by push EBP to the stack. So then we have our buffer. It's going to call the string copy using the str as the input, as the source buffer, and the dst, the buffer, as the destination buffer. Okay, so here this should be 99. So because this is the low address, right? When you copy something, you actually copy from low address to a high address. So this is the direction of buffer copy. So this is the direction of stack growth. So they are in the opposite direction. So because the buffer is copied in this direction, so when the buffer overflow happens, it's going to override the previous EBP and also override the return address. Okay? So when this FO function returns, it will actually pop the return address into a EIP. Okay? So when you do this, so it's going to jump into the location of this compromised return address. So by overriding the return address, so the attacker can point the return address to anywhere it wants, right? It can point to invalid instructions this will cause an exception. Exception is in the x86 is called a seg fault or segmentation fault. So it can also point to a non-existing memory. This will also cause exception, but here it's actually a page fault, right? It will cause a page fault. Then in the page fault handler, the kernel knows there is no memory at this location. It will be converted into a segmentation fault. So it can also point to the attacker's code. In this case, it can execute the malicious code or the control flow hijacking attack. Okay, so here let's draw the memory layout again. So we have there is the str, right? After str will be the return address. So then the old EBP. Then we have the buffer here. So this will be the buffer. Okay. When the buffer is overflowed, it can override the return address, right? It can. So if you look at this, right, when we copy the memory, okay, so it's going to copy more than the buffer, and it will overflow the return address and everything after this up to 300 bytes of content. So here we can put the shellcode. Okay, now when you overflow the return address, you can point this into the shellcode. Okay, by doing so, you can execute the malicious code. So the shellcode is just a fancy name for the malicious code or the attack code. So the shellcode was named as this because normally the malicious code will pop a shell. Okay, it's going to create a shell, so the attacker can sometimes remotely connect to the shell. In that case, that will be a remote shell. Right, on the Windows platform, so you can pop a terminal, or just for demonstration purpose, so the attacker will pop a calculate. Okay, so to demo their attack works. So this is what happens when the control flow hijacking is during the control flow hijacking, right? So we have the buffer, the return address, right? The arguments. So the string copy will eventually copy the content of a bad file from this place to this place. Okay. So when it's giving overwritten, so it's going to overwritten the whole area, this area. Okay. So the return address needs to point to the malicious code in order to hijack the control flow, right? So if you look at this, right, so we needed to know for this attack to succeed, we needed to know what's the difference here. So what's the offset between buffer and the return address, so we can override the return address. And also, we need to know where is the malicious code, the address over malicious code, right? Okay. So here is how to set up the environment. So in the first step is to turn off address randomization. Okay, so you use syscontrol command and to set the kernel randomized VA space, virtual address space, to be 0. So you can this parameter can be set to 1. In this case, it's going to randomize the stack. Okay, it can be set into 2. It can randomize the stack and the heap and the code section if it's able to. Then we're going to compile the program, the vulnerable program called stack.c. Use gcc-g. So this is the debug flag. So you basically say enable the debugging information. Then -o, the output, right? So the output to be a stack. -z execute stack. So it means that the stack is executable. Okay, no stack protector. So this will disable stack canary. Okay, we're going to talk about those defenses later, right? So without disable the executable, without enable executable stack, so your shellcode. So if you look at the malicious code or the shellcode is on the stack. So without enable the executable stack, so the shellcode cannot be executed. So if you try to execute the shellcode on the stack, so it's going to cause an exception, right? So the stack protector is basically set something here. It's called a canary. So when you override the return address, you also override the canary. Before the function returns, it's actually going to check whether the canary has been changed or not. If it has been changed, so it knows there is an attack against the return address. So your attack will also be foiled, right? So, but in this project, we are going to disable the non-executable stack and also disable the stack canary. Okay. Okay, so to launch this attack, right, as we have mentioned, there are two tasks. In the task A, we need to find the offset distance between the base of the buffer and the return address. So we know where to put the hijacked return address. We need to know the distance here, or the offset. In the task B, we need to find the address of the shellcode. So basically it's the address of the shellcode. Okay? So here is the first task. In the first task, so we can use GDB. Of course, because this is a project, right? So we can use all kinds of tools we have. But in the real world, you're not going to have the luxury of you running GDB on the victim machine to find out its offset. Okay, so in the GDB, we do a breakpoint at the BOF. Then we run this program, right? So when you run this program, it will stop at the vulnerable function. Then you can print a buffer, okay? Then you can print EBP. Now, if you still remember this, right? So we have this will be the parameter. This is the return address. Okay. Then we have saved the EBP, but at the same time, the EBP register points to here. Okay. Then we have the buffer. So this is a buffer. So this whole area belongs to the buffer. So if we do the register of EBP minus buffer, the address of the buffer, we get this offset, right? So this will be the distance between EBP and the buffer. Okay. So here is the screen demo. So it's very important to enable the debugging information. Otherwise, the buffer you print here, so the buffer you print here will be a different address, a different buffer. So in fact, it will be the buffer from neighbor C. Okay, so you must enable -G here. Let's take a look, right? Oh, okay. So, and also, if you look at this, right? So the address, the distance between return and the buffer needs to add 4 bytes to this number you get. Okay, so let's do a quick demo. Okay, I have connected to the our VM. So this is to disable the address space layout randomization. Okay, so let's do the GCC. Okay, so this is the command to build the stack.c, a vulnerable program. Okay, we can do a gdb stack. Okay, so we can be. So let's take a quick look at the stack.c. Okay, so the vulnerable program is called BOF. So the buffer size is 24 bytes. It's very similar to the vulnerable program in the slides. So in the main function, we have buffer of 517 bytes. Then we open the byte file. We read the 517 bytes from the byte file. Then we call the vulnerable function. Okay. Let's do gdb bof, right? Set a breakpoint at the bof function. So if you look at this, right? So it says file stack.c 912. So let's open another window. Do the SSH. So here, 912 will be here, right? Okay. Then we run the program. Right now, we hit the first breakpoint, right? Then we can print the EBP. $EBP. Okay, so then we can print the address of a buffer. So the address of buffer will be this. Okay, then we can do the subtraction. Let's do the char star $1 minus char star $2. Okay, let's do P. Okay, so it's 0x20, so that would be 32 bytes. So if we go back to the function, we say here the buffer is actually 24 bytes. So when the compiler allocated memory for buffer, it's actually allocated more than necessary, right? More than needed for the buffer. Okay, so to get the distance between return address and the buffer, we need to add another 4 bytes into this number. So that would be 36 bytes, right? Okay, so let's quit. Okay, this is the first method to find the offset by using GDB. Okay, so the result is a little bit different, right? So because we have different numbers of the buffer size than the slides. So the second method to find the offset is use a byte file with known pattern. So for example, a byte stream over 1, 2, 3, 4, 5, 6, 7 in the binary, right? Then we can enable call dump. So to enable the call dump, so we set a ulimit, the C, the call file, C is the call file size to be unlimited, right? So the call dump is the dump of the process memory when an exception happens. Okay, so we run the program with the byte file. So if we look at this memory layout here, so we have the str, the return address, right? So here will be this will be the EBP. So here is the EBP, and we have a buffer here. Okay, so in this method, so we're going to fill the buffer with a no pattern. So basically, so we have so every slot here on the stack will be 4 bytes. Right, we're actually filling with 01, 02, 03, 04. Okay, so when we continue this way, for example, if this is let's say 21, okay, in hexadecimal, 21, 22, 23, and 24, right? 25, 26, so 27, 28. Now the distance. So the distance between return address, right, will be 25 subtracted by 1, right? So in this case will be 24, 0x24. Okay, so you fill in the fill the buffer with a known pattern. Then when the exception happens, you look at okay, what's in EIP, right? So the exception happens when you try to return from this function. It means that so you are going to jump to the return address to continue execution. So this address on the return will be loaded into EIP. Okay, so when that happens, it's going to cause an exception. Then you can print out the EIP, the content of the EIP. This will give you the offset, right? This tell you where is the return address located. Okay. So let's go to the demo again. Okay, here we have a program called let's go to this one. Click micro offset.c. So if you look at this, right? So we just put a continuous byte string into this file. Okay, so let's quit. We can execute offset. So it will just print out this sequence of the bytes. So if you look at this, right, so there is some printable characters. That's like, of course, we also have non-printable characters. We can redirect this into our input file. Then let's do a hex down -c. Okay, so if you look at here, so this is the let me see, hex down. Let's do the -c file. So if you look at this, right, this will be our input. So from 01, 02, 03 until FF, right? Then we have when we look back, right? So we get another set. Okay. So let's try to execute this. Let's set the ulimit. Let's do the stack. So if you look at this, right, so we have a segmentation fault and it says call dumped. It means we have generated a call file. Okay, so we can use gdb stack call, and then we can p eip. Well, let's do inf reg. So here is the EIP, right? So this is the so this is 25, 26, 27, 28. So the offset is 25 minus 0.01. So that would be 24. 24 is 36 bytes. It's the same result as in the previous method. Okay. So if you look at the segmentation for the information here, so it says that number 0, this will be the call stack. So this is the address of exception. So if you look at this, right, this is the EIP. We are actually try to execute the instruction at this location. So this will cause an exception. Okay. So this is the second method. Let's go back to our slides. Okay, the third method is, we actually have already demonstrated the third method in the previous lecture, right? So we can do a obj dump, destack. We actually disassemble our program. Then, if you look at this disassembler, right? So we first push EBP to the stack. Let's draw the stack layout again. Okay, so here, so the str will be our input, right? Then we have a return address. Okay, then, so this is the state before entering the function, where ESP points to here, right? Then every time when you push something to the stack, so the ESP will move down, right? So we push EBP, so we have a EBP prime here, all the EBP. So now the ESP is actually points to here, right? Then we move ESP to EBP. So our EBP points to this location. So the EBP is the base point, right? So we have mentioned that it's called a base point because you can add up or subtract offset to access the function parameters or local variables. Then we do a subtract of 28 by to ESP. So now ESP points to here. So let's erase the old ESP here. Okay, so this will be 0x28, right? Then we subtract ESP by another 8. Okay, so this is the ESP by another 8 bytes. Then we push EBP plus 8. If we look at EBP here, EBP plus 8, that will be the address of the string. Okay, so it's actually going to read from EBP plus 8. So it's going to copy the content here, the string address, to here. Then we're going to load the address of EBP minus 20 into EAX and push EAX. So here, this will be EBP minus 0x20. Okay, then it's going to call the string copy function. So if we look at the string copy function, right? So the first parameter will be the destination, then the second will be the source. Okay, so we know C, when C pushes parameter to the stack, it pushes from right to left. So this will be the source parameter. This will be the destination parameter. So in our vulnerable program, that will be strcpy buffer and str. Okay, so the buffer address, the address of buffer, it actually equals to EBP minus 0x20. Okay, so it means that, so here EBP, this is a buffer, so the offset is 0x20. So the offset of return address will be EBP minus EBP minus 0x20 plus 4, it equals to 0x24. So this is the third method, right? So we get the exactly same offset. we all get 0x24 from 3 different methods. Okay, so let's take a quick look. Okay, so in the last lecture, I forgot to mention that we can actually use a objdump-s stack. So when we are doing this, let's say redirect this to a stack.asm. Let's do macro stack.asm. Let's search for the BOF function, right? So here, if we look at this, right? So when we execute the obj-s, so we're actually going to do a hybrid disassembly, or a mixed disassembly. It's going to print out the source code and its related assembly instructions. So we need to look at the string copy, right? So the string copy is here. So if you look at this, right, so we loaded the EBP -20 to the EAX and push EAX. So this will be our source, the destination parameter. So this will be the address of our buffer. So the offset is 0x20 plus 4. That will be 0x24. Okay, let's stop here today.